Okay, so this talk is going to be about a simple question that maybe you have wondered about when you took algorithms and you saw max flow and you saw shortest paths, and then you were maybe wondering or opinionating about which of the two is easier, which one, which is easier, shortest path or max flow. And so I'm going to tell you a story of or some line of work that we had on this and some discoveries we found. And so I'm going to tell you the story. Like the first reason I'm telling this is to tell you the answer that we found out. And the second reason is that I think it shows the power of fine-grained complexity and leading to discoveries in algorithms also. So it's not going to be a technical talk. It's more like a story, So sit back, relax, and hope you enjoy. So yeah, so that's the question. What is easier to compute? Okay, so here are two problems, right? In both problems, we get a graph. It's in this case it's undirected. It has edge weights, and we have a pair S and T, source and target. In shortest path, we want to find the shortest path, the cheapest ways to go from S to T. In max flow, we want to push the maximum amount of flow from S to T while respecting the edge capacities. You probably remember that the maximum flow is equal to the minimum cut. So this problem is same as the ST min cut problem. So maybe that's a little bit easier to think about. So you're trying to separate S from T in the graph by deleting the least amount of edges. So in this example, you can delete that cut that's in blue, and you're deleting like weight of 11, and you disconnect S from T, and that's the cheapest way to do it. Okay. So these are the two problems. Now, which is easier for algorithms? So for shortest path, right? Since classical times, we have Dijkstra's algorithm, which runs in m plus n log n. So we have n nodes in the graph and m edges. And yeah, so that's like super fast, and Dijkstra's algorithm is very, very easy, very simple. It's like half a page, and you write it and analyze it in half a page, and that's great. Kind of as easy as it gets. But what about max flow? So for max flow, it took much longer until even to get some polynomial algorithm. And so, right, so I'm going to assume, right, that the weights are in some polynomial range, like always. So there was some running time that depends on the max flow itself. So it was some very large polynomial. And then with the time, it's been improving. Right, so the running time has been improving. And since these works in the last decade, the experts on these kinds of things, these techniques, they use some continuous optimization techniques, some very heavy algebraic tools, and the experts have been telling us like, yeah, it's just a matter of time. In a few years, we will get to linear time. Like these techniques are very powerful. It's just a matter of analyzing them and getting to an optimal algorithm. And indeed, a couple years ago, so there was this paper, m plus n to the 1.5. So if m is up to n squared, right? If the graph is dense, so as a function of n, like this was already n squared. And then 1.5 years ago, in like a breakthrough paper, it was kind of closed. They got a linear time almost linear time algorithm for max flow as well. Okay. And yeah, so if we ignore these logs and the subpolynomial factors, then both problems are linear time. So both problems turn out to be easy. But of course, shortest path was much, much simpler. This is like half a page and super simple. This paper is like more than 100 pages, and it builds on like other papers that are 100 pages, and it's very, very complicated to explain the algorithm and to analyze it and so on. But okay, but at the end of the day, they're both linear time. So we don't have like a separation here. So let's look at some like other settings. If we look at unweighted graphs instead of weighted, well then instead of Dijkstra, we can do BFS. We shave a log. Okay, fine. Here, like nothing much happens. except that even 20 years ago, we could have gotten like n squared time. But anyway, it's still kind of the same. And for both problems, everything I said works for directed graphs also. There's even reductions that show that directed graphs are not harder for these problems. So undirected, directed doesn't matter here. But one thing that is different is that when you run Dijkstra, you're getting more than just the ST distance. You're getting the single source shortest path. You run Dijkstra from a node, you get this shortest path tree, and you know the distance from S to every other node in the graph. And this is not true here. When you run these fancy algorithms, you get for one pair, you get the answer. If you want to know from source to all targets, you have to run it again and again for every target in the graph. Okay? So this leads us to the all pairs problem, the general kind of problem where maybe we can see a difference in the complexity of the problems. Okay, so in all pairs shortest path, we get a graph. There's no SNT anymore, but for any pair like ij, we want to know the distance as if they were SNT. And in all pairs max flow, it's again the same. We get one graph, and we want to know for every pair what is the maximum flow. So in both problems, the output is this n squared numbers. The output size n squared values. And yeah, so how fast can we compute these problems? Okay, which is easier? And in both cases, the trivial solution is you do n squared calls to the ST thing. So for every pair, you just call the algorithms we had before. And you get this n to the 4 running time. So for a single pair, like I'm just removing the parameter m for now, so just think of n. Right? So the linear time thing is n squared for the single pair. So for all pairs, you can do n to the 4. But of course, we know that APSP, you can do cubic time. And this is kind of what I said. You run Dijkstra once, you get the single source. So you just run it from every source. So this is n times Dijkstra, so n cubed. And this is not possible there. For max flow, as I said, you cannot do this. Or you couldn't do this until a breakthrough in 1961 in a very influential paper by Gomery and Hu, where they got the same running time for all pairs max flow as we had here. So with n minus 1 actually calls to a max flow algorithm, for ST max flow algorithm, they can compute the all pairs. So let me tell you a little bit about their work. So they show like a very fundamental result about graphs. It's the following, the Gomery-Hu result. It says that every graph has a cut equivalent tree. And what that means is every undirected graph could be weighted, this G. There is a tree on the same set of vertices. So this tree, T, the vertices of T are the same as the vertices of G, except that it's a tree. So it's a much simpler graph. You go from any graph, you get a tree. And it has weights. It's a weighted tree that could be different from the original weights. And it has a very strong property. It's cut equivalent. And what it means is you can look at any pair of nodes S and T in the graph. You want to know the minimum cut or the max flow. You can look at this same pair in the tree, ask about the minimum cut in the tree. And that's very easy to do. Like to cut a pair in the tree, you have to delete one of the edges on the path. Like to disconnect two nodes in a tree, just look at the path and you have to delete. So in this case, you delete the 11. That's the cheapest edge on the path, right? So okay, so you find the minimum cut in the tree. This is a cut in the graph. It tells you which nodes go to the left, which nodes go to the right. You look at that same cut in the graph, you get a cut of the same weight. It's also 11. And it's also a minimum cut. Okay. And this is true simultaneously for all pairs. So it's like a reduction from the problem on general graphs to trees. So they showed like it's not obvious that such a tree would exist. They showed that it exists for every graph. It's like a fundamental statement about the graphs. But they also showed that you can compute it. So they showed that this tree, this what's called Gomery-Hu tree, can be computed in n minus 1 calls to a max flow. So the proof of they do this is like algorithmic. They say, you start with a graph, you pick a pair, you compute the minimum cut. This defines like a partition. Then you pick another pair, you partition, and so on. In the end, you get a tree. So like by the same proof, they gave an algorithm with this running time. And for us, we want to solve the all pairs max flow problem. This is great because you can just take the graph, compute the tree. Once you have the tree, then solve all pairs max flow. For any pair, look at the minimum cut in the tree. It's easy to compute. You're just trying to find the cheapest edge on the path. As you can do this, like whatever log n time or something, some data structures. So once you have the tree, it's quadratic time problem. But then how do you get the tree? Okay, so the time complexity of all pairs max flow is essentially the time that it takes to compute the tree.
Here, the rate of cut is 11. I have a question. If we delete the 3 edges of S, there are 3 and 4. Vertex S.
Yes.
The edges
Right.
neighbor to it have weights 3 and 4, yes?
Yeah. I think it's a mistake. Sorry. Sorry. Yeah. So in this case, it's not a min cut. Yes, you're right. Sorry. Okay. Okay. And okay, so this is a very powerful thing, right? Having this tree, it implies some things that are pretty strong. One thing it implies is that in the all pairs max flow problem, right, the solution has these n squared numbers. There's only n minus 1 different answers. Okay. And the reason is that in a tree, there's only n minus 1 edges. And every answer is an edge in the tree. So this is something maybe unexpected. And this is not true for shortest paths. If you look at like a clique with different weights, you can have n squared different distances in a graph. Another thing is that like if you cared about like a data structure where you store a graph and you get a query and you tell what's the min cut, this is a very efficient structure. You store a graph in O of n size instead of n squared. So you reduce the size of the graph very much, then you can answer cut queries about the graph. And such a thing is not possible for shortest path. Like if you compress a graph, you're going to lose information about the distances. And you may have heard of all these spanners and graph sparsification results and so on. I think this is historically the first kind of graph simplification result. And the point I want to make here is that, well, so far we were saying, yeah, shortest path is like an easier problem. It's simple and so on. This is like a first kind of anecdote that says, well, maybe max flow is easier. There's something easier about it. This thing that we can compress, there's few answers and so on. These are not true for shortest path. So there's something kind of information theoretically easier about max flow. But this didn't translate into algorithms. So since their work in 61, no one knew how to improve this n factor. So even n over log n or something was not known. Mm-hmm.
When you say cut equivalent, is that only for pairs of vertices you want to cut?
Yes.
And not subsets of vertices?
Yeah, it's only for pairs. Yeah, it doesn't preserve all cuts. It only preserves like pairwise minimum cuts. So yeah, right, for algorithmically, we didn't know how to do anything better than their result. And meanwhile, for APSP, we've seen this list of shaving logs and so on. Like things looked like they were improving. So again, algorithmically, it's not clear which of the two is easier. But then maybe we had some reason to think that if one of them was going to be subcubic, maybe it's APSP. Okay. So back to the comparison, right? Okay, so both n cubed. One thing though is that this works for directed graphs also, this APSP. Here, the Gomori-Hu result is very specific about undirected. For directed graphs, it's simply false. Like it's just impossible to get a tree for directed graphs.
that it is not possible?
Yes, it's proven. One way to prove it, you can make like a graph, directed graph, and then the number of answers will be n squared, like a directed by click or something. But yes, there are like pretty strong proofs. Yeah. So in the directed case, we're still at n to the 4 there. And another thing, back to undirected, if you look at unweighted graphs, what happens? So in here, like, okay, we're still at n cubed. We don't know anything better, except that like we got this n cubed even before max flow was linear time. There's a different way to do it without max flow. But then here you can use fast matrix multiplication. So this is kind of similar to what Nick was doing earlier with the transitive closure and triangle and stuff. It's not quite you need a bit more ideas, but there is like an algorithm that gets all pair shortest paths in undirected graphs, unweighted graphs. All the weights are 1. You can do it in matrix multiplication time. Okay. So maybe that's the separation we were looking for, right? Right. So this is cubic. We don't know how to break it since the 60s. This is subcubic. And that's kind of maybe what we'd expect. Shortest path is easier. Okay, so to summarize what I said, like we had these two problems. For general graphs, they're both at n cubed, but for unweighted graphs, APSP is easier. And the feeling that we had coming into this was that, you know, max flow can't be easier than shortest path. It's at least as hard. So let's try to prove it. Okay. And of course, like, you know, fine-grained complexity is exactly what you try to use. You know, let's just prove that APMF is in this hardness class. So today we saw these kinds of problems like negative triangle and other graph problems that look kind of much simpler than all pairs max flow. Right? And for them, we showed that they're subcubic hard under APSP. So why can't we just show this for all pairs max flow? Okay. And this is something I thought about like since the beginning of my PhD, really. Yes, we did have some results. So not under APSP, but under Seth, we had some results, but only for directed graphs. For directed case, which the Gomori-Hu result doesn't apply, so it's not like the real case. But for directed graphs, we had some separations. So we show like for sparse graph, like you could get n cubed lower bound, where for sparse graph, like m equals n, their APSP is in quadratic. So it's cubic versus quadratic. And under some version of the triangle conjecture, Forkley conjecture, we had a super cubic bound. So we show that you cannot get cubic time for the directed case. Okay. So that like says that yes, APMF is harder, like we expected, but only in the directed case where like it's a very different problem. The Gomori-Hu result doesn't work, so we kind of knew that it's very hard there. So we were not satisfied at all. We were thinking about the undirected case, and that was like really a big open question. Like, can we prove any lower bound? Like, we didn't have any lower bound. There was just even 2.1 or something we didn't know. And here's where I want to give like credit to fine-grained complexity. So like, you know, 10 years ago, like this is a list of problems that I liked and I thought are fundamental and interesting. You know, for each one, there was like, yeah, decades of being stuck. And if I, you know, woke up in the morning, you know, I could have picked any one of them, and I wouldn't have found it reasonable to spend like a year or two thinking about all pairs max flow. Like, I would have just been too distracted by all the other problems that I could have worked on. But then, right, there were all these reductions and so on, and I realized that this is the picture. Like, yes, we have the red ones. These are the conjectures. These are like, you have to be very brave to work on them. But then everything else is like, you shouldn't work on them. Until you break a conjecture, those are done. And then all pairs max flow stood out as like, in this kind of list that I had, it's like worth studying. Okay. And then I also want to give like some kind of technical credit to fine-grained complexity. So there, this is something that Nick will talk about on Thursday. So I'm just going to give a teaser about this. So when we would like to prove reductions, let's say from SAT to threesome to APSP and so on. So there's some barrier that people have suggested for proving reduction. So it's a barrier that says that there's no reduction. And it's based on some non-deterministic algorithm. So if you show some non-deterministic algorithm for a problem, then you can use this to deduce that there's no reduction. So Nick will tell you more about this on Thursday. But the point is, like, we knew this barrier and we couldn't prove a lower bound. So we said, let's show a barrier. Let's give an excuse for why there is no reduction. And we did that in a paper some time ago, where we came up with some kind of protocol where a prover proves that this is a Gomori-Huttri of a graph and it's efficient and so on. So it's like a hypothetical model. We were really using this as evidence, like why there's no lower bound. But then, like this had some interesting ideas. So we started thinking, okay, did we really need this non-determinism, or can we get a real algorithm? So then, sometime later, we had another paper. We had a bunch of results, like we solved the problem with approximation and so on. We were happy about this. And then there was one result that, we were not excited about at the time, but later realized it's like really cool, is that we had a reduction from like this, what we had in the previous slide is actually a reduction from all pairs to single source. So for all pairs max flow, we showed the reduction from all pairs to single source. And then we just focused on single source. Like whatever time you get for single source, you can get for all pairs. And then in this paper with Robert Krautgamer and Ohad Trabelsi, we got the first subcubic algorithm for all pairs max flow, only for unweighted graphs. So the running time was this into the 2.5. So it's the first improvement in 60 years. We were very, very happy and so on. But like, okay, in terms of like the separations we were looking for, this didn't change anything. It's still like 2.5 is still larger than the n to the omega. Okay? But it still started to shake our belief that the cubic is like the barrier for the problem. And yeah, one of the tools we discovered was this isolating cuts. I'll mention it later in the talk. And then 6 months later, there were 3 papers on arXiv at the same time, improving the bound from 2.5 to n squared. Okay. So that was kind of strange. Like, I mean, okay, first of all, for the first time in history, all pairs max flow was easier than all pairs shortest paths, which is very strange, maybe. And then also, like, this is like essentially optimal. Like the answer has n squared values, and you can just compute all of them in n squared time. And it's kind of like this is the time for computing the ST, one pair. We compute all pairs in the same time. So that was great. But then we got greedy, and we wanted to get like truly linear time. So if the graph is sparse, like we don't want to spend n squared time computing all the values, it would be good to just go in linear time get the tree. The tree has linear size. So if you just get the tree, then you can ask any queries about it. So like the real holy grail would be to get m time, not n squared for this problem. And yeah, we didn't think this is possible. We showed some lower bounds. So we showed that like this is not possible for unweighted graphs until you break the cubic bound for general graphs. So this gives further motivation for the question of general graphs or weighted graphs. And an even better motivation maybe is that, like, okay, we want this separation from all pairs shortest path to all pairs max flow. But then, as Nick was saying, just like the experts on max flow were telling us, yes, it will be linear time in a matter of years. Many experts on matrix multiplication say omega will be 2, like just a matter of years. So maybe in 100 years, this is not a separation. Both will be n squared, and okay, both problems are easy. Maybe that's not surprising. But then, for weighted graphs, if you solve all pairs max flow faster, then this is like a proper separation because we have this conjecture, right? APSP is not in subcubic time. This is a conjecture that the experts somehow believe in the sense that we don't have any kind of line of attack that would make it subcubic. so then what happened? So then we joined forces with some of the other people who were working on this, and we wrote this paper. We got a subcubic bound for all pairs max flow in general graphs. And 3 weeks later, we realized it's actually n squared time. And Tianyi Zhang observed the same thing. So this is with Robert and Dohad and Jason Lee, the Malia Panigrahi, and Tachefol Sarah Nurak. So assuming the APSP conjecture that the n cubed is not, it's a barrier for APSP, we get this separation. That's like the opposite of what we thought should be true. All pairs max flow is much easier than all pairs shortest paths. So if you still think,
Is it still true that this is only for undirected or directed graphs?
only undirected. No, for directed, we have lower bounds. Yeah, so if you still, really believe that max flow is a harder problem, then maybe you should doubt that.
So now, near unweighted is possible?
Yeah, so that's the next slide. So yes. So then, we wanted to get this, to get linear time, and then we also got it. So this is you can run in linear time, like super fast, and then run in make polylog calls to a ST max flow algorithm. So essentially the same time for an ST algorithm, ST max flow, which is linear time, we know. You can compute the Gomori-Hu tree, from which you can get all the answers. So the title of the paper was that all pairs max flow is no harder than single pair. Okay, so that's like.
I'm assuming this is near max flow that was something.
Yes. Yeah. It's just like some kind of algorithmic analysis of the graph with like kind of like the Gomori-Hu algorithm where you find cuts and you recurse and so on. Just we do it in a certain way. Like the pairs we choose to make the cuts for is like cleverly chosen in a certain way. But at the end of the day, we're just making calls to minimum cut, ST minimum cut, which we use this 100-page paper to get. But you could have used any of the like slower algorithms. Like there are subcubic max flow algorithms that are simple, so you could have used them and gotten like a simple subcubic algorithm. Yeah, so I'm not going to go into the proof of this, but I just want to kind of highlight that. So like the techniques we use to get this result are not like fancy. I mean, as I was saying, like even you don't even need all the developments on max flow to break the cubic bound. Like we could have broken the 60-year bound with like combinatorial max flow algorithm. Well, we did use on top certain tools that were designed in these years, but it's all like elementary stuff, relatively speaking. And I think really the contribution was like the lower bounds, like knowing which problem to focus on, and then moreover being always guided by these lower bounds, these conditional results that we're proving along the way. And I'm going to give you one example of what happened. Like it might not make much sense because I'm like this is like deep in the proof what's going to happen here, and like maybe you will not have the right context. But let me just show it. So when looking at the problem of computing the Gomori-Hu tree, we were saying like, what if the graph looks like this or like that? What can you do, and so on. And one of the hard cases that we were stuck on for a long time was when the Gomori-Hu tree looks like this. It's like a very simple looking tree, but like very complicated to find. This is not the graph, this is the tree. So like the graph could be pretty rich and so on. And like we were looking at this and we were thinking like this is like a triangle type of problem, and we know that triangle problems are hard and so on. So we were really looking at this as if like this is gonna lead to a lower bound, because we wanted to prove a lower bound from reduction from triangle. And it's like, conceptually, it's like you have a graph and you want to decompose the graph into triangles such that like the sum of the weights of everything is kind of maximal or something like this. This is the problem. And yeah, we focused on this, and we got an algorithm, like some kind of lemma or tool or something called isolating cuts that solves, like, we designed it specifically to solve this case. And this tool, I mean, it was independently discovered by these guys for work on different problem, but these papers came out together, and this tool has been super useful. Like in a year or two, like there was more than 10 papers using it for a bunch of cut problems. And for all these developments on Gomori-Hu, this was like the key thing. So just like an example. And I just want to end with a slide saying, like, this is not that rare. Like, since fine-grained complexity have been like blossoming, improving all these results, and looking at like questions, like there were like questions that are like famous, very famous problems for which we were trying to prove lower bounds and failing, and then someone comes up with an algorithm, and it's like a big deal. And you cannot prove that like these people wouldn't have come up with these breakthroughs without the fine-grained complexity. Like, can't prove this formally, but like this is certainly how I feel. And so here are just some examples of some best paper awards in the last few years. Like for edit distance, this is like a string problem. We'll talk about it on Thursday. Like we knew that solving it exactly, you need quadratic time, that we can't do subquadratic. Then we were trying to prove that even approximately you cannot do it. And then there was a breakthrough getting a constant approximation, subquadratic time. And this is some invented new technique that led to a lot of breakthroughs and so on. Another example is computing the diameter of a planar graph. So the diameter is the largest distance in the graph. On Thursday we will see, or tomorrow we will see that if you have a sparse graph and you want to compute the diameter, you need quadratic time, assuming strong ETH. So then we're saying, okay, what if the graph is planar? It's a planar sparse graph that has certain structure that you can draw it on the plane, something a lot of people work on. And yeah, then it's an open question that was raised many times by fine-grained complexity, and then Sergio Cabello came up with some really nice technique, and he broke the quadratic barrier. And then this technique found many other applications in planar graphs. And a couple years ago, there was a paper on matching in dynamic graphs. So yeah, that's it.